And get the presentation shared, and then I can turn the floor over to Tim.
Okay. This is obviously a little more nuclear mature audience than I'm quite frankly used to. So I think the best thing to do is be through the chat. Maybe I'll try to interrupt the presentation with the questions so that we can get to the information that everybody is most interested in. And I'm gonna, depending on how the time works out, I may have to jump through some stuff to make sure that we try to remain within an hour. But overall, what I'm going to try to do, and even though the maturity of this audience is, like I said, more than what a lot of times I end up talking to, I want to go through the why. So the why part of why are we working on new fuels? Then we'll get into the what, some of the specifics on some of the fuels that we've worked on, and then into the wheres, which is the facility, and ultimately at the end, a brand new facility. So go ahead and go ahead, forward it or jump to the next slide, Joe. Okay, so our mission, and this is a general statement, and I'll say that it'll focus on, this presentation will focus on our division or my division. But as the wheel shows up on the upper right, it's all integrated with the entire nuclear research enterprise of the INL. But for fuel specific, the goal is to increase fuel performance for existing reactors and then develop new fuel options for a wide range of reactor designs, which a lot of people probably know in this kind of an audience. That is pretty extensive. I've got a list that came out in a publication that there's between, you might as well say between 20 and 30 developers working on concepts that use a wide range of fuel systems. The challenge, as you can see in the box in the lower right, is that each one of these fuel types requires a different piece of equipment. So our floor space within our division is quite extensive. We have 5 facilities within our division, and then hoping in the future to get one even larger new facility. And I tease the people that are in characterization by saying that, you know, for us, the reason we need more space is everything can't be broken down into a little itty bitty piece to fit into your SEM. So we've actually got to build the real thing. Let's go ahead and advance. And I stated up front that I wanted to get into the why, even though for this audience, this is potentially review, but I think it's important to bring up in the context of what we need to talk about and why we're doing what we're doing. So all solid fuels, and we put that in there because we now are starting to work on molten salt type fuel systems, are made up of the fissile material, which we call the form or the fuel meat, and the fission product barrier, which is the cladding. And ultimately that forms the fuel system, which we call the form. So the fuel form, and you'll see that in some of the upcoming slides. A couple things on the engineering front that I think are important to emphasize is that the fuel system overall needs to operate as high a temperature as possible, and that all depends on its reactor design. Stay in the reactor as long as possible. And again, a critical engineering parameter is remove heat as fast as possible. And then another component that we're starting to deal with is taking advantage of the design options for fuel systems that go above 5% enrichment, which in large part that has never been really utilized in a commercial sector and generally only utilized at this point in time in the research reactors. An important note that I put there at the bottom that on a physics and engineering scale is that the core total U-235 density matters more than the enrichment. The licensing and the controls are associated with enrichment, but if you have a denser material that has more uranium in it, then that means you can have more U-235 in your core. And if your heat dissipation rates and what you can design with your core can have more dense fuel stacking in it, your core is better off because you have more U-235 in your core. Go ahead and advance. So some considerations relative to the fuel. And if you start on the left-hand side for the mission envelope, that's essentially your design parameters for your specific reactor. One of the challenges that I bring up as an analogy relative to this kind of parameters is a reactor. The analogy is a vehicle. So yeah, I want to design a reactor. Well, you want to design a vehicle. Well, with a vehicle, do I want to transport thousands of pounds of material across the United States, i.e. like a railway system? Do I want to go from 0 to 50 in just a couple seconds? Do I want to fly people across the country? All those are vehicles, but they all have different design parameters and they all have different fuels. But jumping to the thermal conductivity, I mentioned that earlier, that being able to get heat out is an important engineering consideration for fuel and how the reactor is going to operate. For the fuel specifically, the mechanical and geometric integrity is important, meaning it doesn't want to fall apart when it's under irradiation or the conditions of that specific reactor. The stable and predictable behavior, that's intertwined with all I'll say the nuclear research cycle that usually is encompassed with fuel behavior or fuel performance. So how is it going to behave in the conditions in that reactor? How is it going to behave in upset conditions, with swelling, blistering, corrosion, all those kinds of things factor in. And then for us as an organization and fuel specific, the fabrication process, it needs to be designed to allow consistent fabrication. We'd run into scenarios where people can envision something, but you can't build it consistently. Those of you that know about even stuff that was built consistently for decades can still run into hangups in the fabrication process. And those of you that know about the Hyde core problem at this point, whatever it was, 18 months ago, maybe a little longer, been making it for an awful long time, but something happened in the fabrication process. And then, like I said, referencing the overall research cycle in the center, testing to verify performance. At this point in time, it's decades long. And quite frankly, you could argue that there hasn't been anything new actually fully qualified in a long time. That's not a completely true statement, but we really haven't had anything new produce electrons on the grid for quite some time. So getting to, like I said, how do you break it up so that you can talk about such a wide range of fuel options? And so these are the primary 4 fuel types that we talk about. So the particle fuel, plate type fuel, rod fuel, and now we're getting back in where I need to address the molten salt fuel systems. A lot of this crowd probably knows this, but the picture in the very center, the particle fuel that shows up in all kinds of publications and in even this presentation, that's actually a failed particle. But the failed particle actually shows the layers of that. So it's really used a lot to be able to communicate about that particular fuel type. Go ahead and advance, Joe. I kind of referred to it earlier, but I think it's important to point out that worldwide, the vast majority of commercial reactors use fuel rods, but in a very narrow bandwidth of technology. So it's less than 5% enriched U-235, that's uranium oxide, and it's in some form of Zerk cladding. So that's all the PWRs, the BWRs, the CAN-DOs, the Russian systems, basically everything. The vast majority, there is some in France that do use a mixed oxide fuel, but for the most part, it's a very narrow bandwidth. And like I referred to at the beginning, our goal is to try to give options even for this kind of a fuel system and expand options for other kinds of cores. It's also important in some ways to, in terms of the overall story that we're trying to do, you can look at the sheer numbers here in terms of bundles and pellets, and the commercial production of these is in the millions of pellets per year. And yet a lot of our research might be in the dozens of pellets to be able to send an irradiation to ATR. So somewhere in our future, there's going to be a jump from these concepts that we're trying to develop enough data behind to qualify to being able to demonstrate how you fabricate them at scale. Go ahead and jump, Joe. And starting to discuss, you know, what options are out there and how do we expand what is potentially available. So it might be, it's considered a rod form, but the shape of the rod can impact, like, for example, the light bridge reference here, you know, that shape in effect increases your surface area. So you're impacting your ability to conduct heat out of the system at a different rate than just a tube with a solid oxide core, oxide fuel. You can get like the variations at the upper right that is very similar to EBR2. So a rod that's got a wire coil around it. Obviously that changes your packing density. Now in that case, it's a fast reactor. So you do have the design options to get your fuel more increased density. But where this is important still is the natrium reactor has a very similar system that it is designing for its fuel. And then you get into the options that we'll start getting into the fuel meat specifically, but in the lower right, you can see some of the work that we did related to, rather than a solid casting or a solid fuel inside the rod, what happens if you have something that's annular? And then how do you actually fabricate that is one of the challenges. But again, the annular is associated with the engineering of getting heat out and distributing where your fuel hot zone is, your centerline temperature in. So if you take a slight step back, uranium oxide and most solid fuel forms, the fuel centerline temperature is the hottest part of the fuel. And because of that, you tend to get product distribution or migration over the time in the reactor, because the temperature gradients are a driving function for having things move. If you have an annular fuel, that changes that whole dynamic and potentially can improve your overall situation, i.e. it can stay in the reactor longer because your fuel has a more consistent behavior. Go ahead and jump to the next slide. As it says at the top, particle fuel is not actually a fabrication capability that we have here at the INL, but it is something that we need to talk about because it's an important fuel system for a number of upcoming demonstrations. To the credit of the INL over the past several decades is what is now the ART program, or I believe that's still their acronym, did a significant amount of work qualifying this fuel type, and some of it's still ongoing here within the INL. The history of the fabrication is, recent history is development work at Oak Ridge, transition to BWXT, BWXT has made most of the last fuels that were tested in the ATR, but because of their qualification program, like I said a little bit earlier, this is a sought after fuel for a lot of the developers. Some that know Pele. So the DoD based reactor that is intended to be deployed and tested for the first time here in the dome is a particle fuel. X Energy is an entity that is looking to expand its particle fuel fabrication capability. Another one that's off the top of my head is USNC. Their concept is also particle fuel based. But like I said at the top, we don't actually have this capability at the INL right at the moment. Go ahead and jump to the next. Plate type fuels. So this is something that's important to talk about. The INL had a long history going back to what used to be the RERTR program, so the Reduced Enrichment for Research and Test Reactors, which was the NNSA-based funding or program to convert HEU-based test reactors into LEU or HALEU. And so the INL developed quite a bit of capability in both the dispersion fuel and the monolithic. And simplistically, it's fuel that is formed into a sandwich, and in this case, the green sandwich is the what forms the cladding. Go ahead and jump and we'll show you some of the capabilities. So to produce the monolithic, basically you need to end up producing a foil of a uranium-based alloy. The lab has in the past done U-Zirc and lots of U-Moly, and ultimately the program that went with U-Moly. So it's a uranium moly alloy that goes through a sequence of rolling to ultimately get it into that plate or foil, excuse me, that then goes into the fuel. Go ahead and jump the. Also the ability to do the dispersion. So the dispersion, as you can see in the lower right, you know, a uranium aluminum fuel in an aluminum mix, then surrounded by an aluminum cladding in this particular case. So you start with a compact like in the upper right. That's of the uranium aluminum alloy and the aluminum. You put that into a roll, and then basically you squish this stuff out to get to the ultimate, like in the lower right picture. Go ahead and jump. I kind of talked about it a little bit, but plate fuel almost exclusively is for research reactors. And a couple examples here, and obviously the ATR one is near and dear to the INL, but that's one of the elements for that reactor. And then you can see the picture of a Hyfer core. Now the Hyfer core, if you pay attention to the picture in the upper left, you can see a person's hand. That gives you a scale. That core is not very big. It's awful close to the size of a beer keg. But as you can see, in terms of where all of the plates are curved one way in the inner core, curved another way in the outer, it's a very complex fuel. But again, need to mention it as a capability. The program, the HPRR program, as it's called now, High Performance Research Reactor, most of their work has gone beyond the INL development and is now transitioned to BWXT. But there are still samples and experiments that were related to work done at the INL that are still in the process of the INL research cycle. So that's why I continue to bring up this as a capability that we retain in at least segments now within our division. Oh, yeah. So trying to get into a discussion in terms of the fuel forms or the fuel meats. The challenge is it's a huge array. It's like saying, I'm going to talk about material science. And so it's pretty open-ended. So we've worked or try to maintain the capabilities to work in all of these different types of fuel forms. So the intermetallic, one of the best examples that the lab's worked on is the uranium silicide fuel system, and that's a pellet there in the upper left. It kind of looks like the picture went a little goofy on us, Joe, but we have a lot of metal fuel systems. So the metals, different alloys that we cast, extrude, do other things that we'll talk about later. The ceramic, which I already mentioned, the UO2, but we've done a lot of work with the uranium carbides, nitrides, and I'm going to point out later, we try to maintain the capability depending on the concept that somebody comes up with that we can still fabricate that particular pellet. And then in the lower part, start talking about the dispersion. So there's a lot of concepts that might be a fissile component in the case up there, the UO2, but with a non-fissile component, beryllium oxide. And in this particular case, we've actually got a Endeavor, it's the right way to talk about it. So there is a reactor down at Sandia National Lab that is interested in extending its life, and it happens to be a UO2 beryllium oxide fuel meat in that reactor. Biggest thing to point out with all this is there's a wide range of options once we start getting into the actual fuel meat. And again, going back to what I mentioned earlier, the important thing is what's the reactor design? So what temperature at? What is the cooling medium so that my fuel meat and cladding system can survive in it? And then can I fabricate it? Go ahead and jump forward. So a lot of the ceramic based processes are on a simple level, and trying to talk to here is a powder base. So you're going to create your powder, mix your powder, add a binder as if it's needed, press it and sinter it. Now, there's an awful lot of work behind this, and one of our participants, I know, just actually completed her PhD with work that is represented here. And to say it's simple, she would probably, if she was close enough, hit me with a stick. But what you're seeing here is a glove box that we've set up, and inside there you can do all these processes. You're going to see in some of the follow-on pictures lots of different glove boxes. There's two reasons for that relative to application to nuclear fuel. One is for elimination of oxygen. So let's try to keep our samples from oxidizing to the extent possible. So it's, I'll say, scientific cleanliness, and for radiological control. So obviously our mission is generally associated with uranium, although plutonium related and other actinides in other facilities. But the challenge is with us is, yeah, I got this concept, it makes a pellet, or I got this concept, it casts this, but I got to do it in a radiologically controlled environment. And so that's why lots of pictures of glove boxes. How do you design your sintering furnace to come up in the underside of the glove box? In this case, you can see a rack of sintered pellets that in this picture, if I remember right, is actually uranium silicide. And then going over to the right, we've set up the capability to, once those pellets have been sintered, to grind them to within the tolerances that are needed for whatever the follow-on, either experiment or sliding it into the rod, whatever the case may be. But you basically have to provide the full range of these capabilities just to be able to have a pellet that can then go inside its cladding to be tested and irradiated. go ahead and jump. Getting into the casting capabilities, the INL and then formerly Argonne National Lab we basically are the forefront of most metallic fuels, definitely in the United States. So we have a lot of experience in terms of how to do it for, in the case of EBR2 was a metal fuel, and that's where the injection casting comes in. But what you see in essentially the center left is a arc melting system. So if you don't know that technology, it's a modified welder. So control your arc and put in your constituents that you want to melt together. It allows you to go to very high temperatures. You can create a lot of different alloys. We've taken that and also made it so you can injection cast from the bottom, so you can create something other than a button. You can create a slug. But one of the limitations of this particular technique is temperature control is almost impossible. It's actually an art. So you can't control your superheat particularly effectively, but you can sure create an awful lot of different things with it very rapidly. And so that's why as you transition to the left, or to the right, excuse me, in the lower, you can see a casting system, although it's inside a vacuum chamber here, that was developed here in order to be able to give us more control of temperature so that you understood better the behavior of the alloy that you were working with, and to increase the volume that you could be, the mass that can go on. So that casting system can do, on the scale of 2 kgs at a time for that particular alloy. Injection casting is, other than, like I said, I could argue that the arc melter has an injection casting capability, but we don't have a traditional injection casting capability at the lab like we used to during EBR2 production days. But there is a lot of design work going on. That's actually the technology and the technique that the virtual VTR reactor was going to use. So there's been a lot of new design work to modernize the concept. And there's a high probability that the natrium reactor will use that technology, because there is such a history there with how that fabrication technique translates into reactor performance. Go ahead and jump forward. Another technique relative to metal that we have established the capability here at the MFC and the INL is extrusion. So one of the challenges with the injection casting is you got scrap associated with the quartz mold. So is there a way to fabricate fuel that doesn't have that kind of a scrap rate, but allows you to create a fuel that has a consistent behavior and gives you the same properties in terms of all the data associated with that fuel's performance? And the INL, in conjunction with TerraPower at this point, probably 10 plus years ago, established the capability to do extrusions on uranium. And you can see the picture there, a younger member of our staff standing in front of the extrusion press. If you don't know this technique, it's similar to like the graphic that's on the left. It's what's used for aluminum. Lots of people know about aluminum extrusions, but it's still effectively the same process. You just apply it, in this case, to a uranium or uranium alloy. So cast the billet, machine the billet down to the tolerances you want. Behind Brady and slightly out of sight, is a uranium or a molten salt heat bath. So you heat it up in the molten salt, bring it up to temperature, swing it around and put it in the press and extrude it. And that's what you see in the extrusion process. So basically you're squishing it through like a tube of toothpaste, although it's technically way more complex than that. And you can end up doing solids, you can do tubes. There's a number of things that this technique is good for. Currently, our work in this area is associated with the second generation natrium fuel, and they are actively working with that ARD funded program to develop an extrusion technique for, like I said, it's my words, our second generation natrium fuel. Jump to the next slide. New areas that we're looking at is underneath what we're calling advanced manufacturing and additive manufacturing. And to me, the important thing that we're working on here is to bring in new techniques that expand design options that you can't do with traditional fabrication techniques, or haven't been able to be used in the past and haven't been able to be demonstrated on uranium. So underneath advanced manufacturing, you'll see some CERMETs and CERSERs. That work was actually associated with NASA. So if you don't know, NASA's got, from my perspective, two thrusts, one associated with propulsion and one associated with base power. So the propulsion ones are what you see here, and that's why there's holes, because the concept is during, while it's critical, running hydrogen gas through the fuel, obviously that I'm approaching it simplistically, to generate your thrust for your rocket or your spacecraft once you're up in space. The SPS that's mentioned here, spark plasma sintering, is the techniques that's the advanced manufacturing capability that we've established here that has allowed this to happen. Spark plasma sintering, simplistically, is under pressure. You apply an electrical field and do a densification in such a rapid way that you have microstructures that you can't create with a thermal sintering process. So that's why the uranium nitrides, in conjunction with the tungstens or rheniums, you don't destroy the properties of the uranium nitride while you're getting up into temperature, that you can still sinter the tungstens or rheniums. And that's actually same to true with the zirc carbides. Jumping to the right, additive manufacturing is something that we've been hoping to get into, work through some process or some challenges over the last couple of years, and are now to the point where we can take advantage of what additive manufacturing might be able to bring relative to actual fuel systems. And I already talked about the SPS, and it's still being worked, but what you see at the bottom picture on the right is a pellet that was started being formed with a lens. So the lens is laser engineered net shaping, I believe is the right acronym. But the technique is using a laser, injecting powder through a gas process, and then building up what it is that you've programmed in. So in this case, the first goal was a pellet, but you can do a bunch of different things. You can try to tailor your porosity differently than if you were just trying to cast or do a powder metallurgy process to your pellet. And then obviously you can start to get into different shapes. What happens if I can transition from fuel into cladding with the same process? A lot of these have yet to be really, I'll say, tested or brought to practice. But opening up the design options was one of the big things that we wanted to do with these additive techniques that we have looked to deploy. Go ahead and jump. Got to start talking about molten salt. One of the big ones that's talked about here is McCree. So one of the ARD funded projects that is, again, another branch underneath TerraPower, is they have a concept that uses a molten salt reactor ultimately to produce electricity. But along the way that they need to do for their overall goal is there's still some unknown things associated with how the fuel is going to behave And in this case, it's a chloride fuel. So it's uranium chloride fuel. And so that's where this McCree reactor is designed. And the current scenario is that the fuel will be fabricated here at the INL in the fuel manufacturing facility. The reactor will be built and brought together inside what is currently zipper cell, and it will be tested there. One of the unique things about this particular fuel, and I've talked about enrichment a little bit in the past, but one of the things that the INL and DOE brings to it, this is actually an HEU fuel. So in order to get the experiment data that they need HEU to do this McCree. It's not what's going to be, HEU is not what's going to be used in the production model that's intended out in the future. But nonetheless, that's what we're going to be doing for McCree. Go ahead and jump to the next, show you some of the pictures that I stole from them. And so working with TerraPower, they've started working on uranium salts. At one point in time, there was a discussion that the McCree experiment was going to be a plutonium salt, but that had some very serious complications just with where do you get your plutonium. And currently the way the development is working, other organizations, not just ours, although they'll be working with my organization, will be working on the fuel synthesis process in FASB, working on how to scale it up and design the scale up furnace that will then be deployed in FMF. And then that's where we'll go through the production. And it's several hundred kgs of uranium chloride salt that will need to be produced for that McCree experiment. Go ahead and jump. And that's what I was nervous that we were going to run out of time, but trying to get into the wheres of where all this stuff occurs, go through the 5 facilities that are in our division. So the fuel manufacturing facility, and that's what you see there in the picture, is looking down what's called the AFCI glove box line. There's more to the facility, but the things that are important is security category or safeguards category 1, which means you can have a lot of HEU or a lot of material out. HAZCAT 2, for the INL, it's our primary facility that if the fuel contains plutonium or HEU, like I mentioned earlier, relative to McCree, this is the facility where you would need to do it in. There's still a lot of other capabilities in there. In this case with the glove box line, that's where a lot of work was done for minor actinide containing metal fuels and oxide fuels that at one point in time, there was an increased emphasis on how those fuels were going to be behaving, and that's where it was actually fabricated. Go ahead and jump. The former zero power physics facility, we still call it that. And what you see there is the picture of the cell. Current plan is to go through the DOE 413 process and evaluate options for demonstrating reactors that do need HEU or something that requires a high security category around them. And the likely pathway is to turn the cell that you see there into the Lotus reactor demonstration facility. There's a lot of design work going on now. How do you get things in and out of that, when somebody's going to build a reactor somewhere else? But not shown in the picture, the zipper facility still retains a lot of materials in vaults, and that we need to actively monitor, if you will. And that's actually the source of a lot of the things for us in terms of feedstock. So somebody wants to do something with that requires a fair amount of uranium, we still have that in the vault, and we still need to monitor what's going on in the vault. Go ahead and jump. So advanced fuels facility, I mentioned earlier the spark plasma sintering system. And that's actually what you see in the forefront of the picture right here, with a couple people working on it. And I believe one of them is James, who's on this particular call. And then in the background, you can actually see a laser welding system. The biggest thing to point out for this facility is this is where we do intend to deploy any of our advanced or additive manufacturing processes. We've worked over the last several years to give us more square footage, and this facility was upgraded via suspect exhaust and just literally HVAC for human occupancy. And it's already to the point it's probably 3/4 full. Go ahead and jump. Another one of our facilities is the Fuels and Applied Sciences facility. This particular building has increasingly become multi-program. We've expanded a lot of the characterization capabilities in here. And that's kind of what you can see in the center picture, and then see the research scientist working on sample prep in the right picture. So we still retain the ability to make some fuel samples in here, but if you want to do the polishing and the things you need to do optical evaluations, SEM evaluations, and other things, this facility is where a lot of that occurs. There's also the IANS system is in here, which is mini hot cells to do corrosion testing on irradiated materials. And then I had mentioned earlier about the McCree synthesis development, and that is occurring in a new glove box that is in this facility that is known as the PCG, pyrochemical glove box, pyrochemical separations glove box. And it's actually one of the newest and the largest glove box here at the MFC. And there's numerous furnaces in there, some associated with weight development, but a lot of them are associated with molten salt capability expansion. Go ahead and jump. Experimental fuels facility is another one of the radiological facilities in our division, and it's largely broke up into two halves. The one half has the powder processing capability that we talked about earlier, and then on the right you can see a 2-story system that is actually a brand new system that is being installed. That is a multi-kg atomizer. So we'll be able to produce metal powders of uranium and uranium alloys on the multi-kg scale that will open up, like I said, a lot of opportunities for whether it's advanced or additive manufacturing. It's a powder process that somebody's come up with. Again, a pretty major capability that's going in there. In the center picture, I didn't really talk about it extensively yet, but we have machining capabilities both directly on uranium alloys. So to be able to put it in a mill, be able to put it in a turning center, do EDM on it. And I did talk about the centerless grinding, and that's actually in the center picture. And then on the far right of the center picture is an area that is a general machining area, not for machining directly on uranium, but potentially machining on things that contain uranium. So say we make an experiment on a rod, and in the welding process, it didn't quite meet the tolerances. Well, this is an area that we can bring it into, machine it down into the exact tolerances that are required for the experiment. And then on the left, I mentioned during the extrusion process, the molten salt bath to bring the material up to temperature. And that's what you see in the center of that picture, is that glow is the molten salt. And it's in the 600 to 700 degrees C range. Go ahead and jump. To me, this is one of the most important things for the future of the lab and the future of all these demonstrations, everything that I talked about was associated almost exclusively with, the research scale that we need to do. Let's create this fuel, test it to the point that we want to do something further with it. Well, the further with it is an engineering scale demonstration. It might be a lead test assembly to go into an existing reactor. It might be the first core of one of the new micro concepts. But one of the biggest challenges that we have is we don't have any space to do that. And in the future, we need an engineering scale facility in a HAZCAT 2 situation that allows us to do potentially hundreds of kgs of material in a process. Obviously, there's crit limitations and enrichment, and fuel type is going to impact that. The good news is right at the moment, for this facility, we've started the discussions with DOE to enter the 413 process. We've submitted a draft CD0 statement in terms of establishing the need within the complex to do this kind of thing. And there's a request into the FY23 budget to be able to have enough money to start doing the design of this facility. With the scenario being that once SPL is done out here, that you take the money that's being invested in the SPL construction and then you translate it into this new facility. And so ultimately, this culminates to me the importance of, for reactors, rather than just research, we got to get to the point where we demonstrate something new. As a lot of this crowd would know, we haven't built a new reactor in 4+ decades. And it turns out to build a reactor, you just can't do a paper design and say, insert fuel here. You actually got to be able to build the fuel and build it in quantities that allow you to assemble and have your reactor for demonstration. So I guess I ended up going fast enough after all, Joe.
Yeah, timed it just about perfectly. Now, don't see any questions on the chat. If you have any questions for them, go ahead and type those in there. Let me actually stop sharing my screen here so they can see you. I had a question. Is there any location in mind that they have for the new fabrication facility, or is that still way too far out?
The conceptual location right at the moment is to the north side of the Pietas. So where office building 717 is, right in there, like I said, on the north side of the Pietas is where we're currently thinking.
Okay, and then, well, just since I worked out there, and it's really exciting to see all this development, all the new facilities going up that were just on the wish list or in the in the conceptual stage. It's really exciting to see the progress. I think you covered everything really well. We don't. Oh, wait a minute. We just got some questions starting to come in on the chat. So what type of components besides fuel pellets do you see using with the lens, the acronym LEMS?
I mean, part of it depends on the design. We have talked about a ZERC transition. We've also talked about a couple other things. Actually, can you make a ceramic liner between the fuel and the cladding? So I don't have a straightforward answer to that one. There's been a number of things that we've talked about conceptually. And then, as a lot of people know, you come up with your concept, then you try to lobby for funding to pay to see your concept through.
Okay, very good. We did have a question earlier, just to let everyone know, we will make the recording of this presentation and the slides available on the ansidaho.org website, just as soon as we can get them posted. And then with that, I think we can go ahead and wrap up. So
well, that was a pretty easy crowd, considering some of the names that I can see on here.
Yeah, so I'm surprised they're not giving you a little bit more grief.
They'll just do it later.
Yeah. All right. Thank you everyone for attending, and stay tuned. We're gonna, we've covered the fabrication side of things, and as soon as we can later this spring or maybe into the summer, we're gonna catch the other end of the equation and talk about the new PIE, post-radiation examination capabilities. So stay tuned. And thanks very much.
Okay, thanks, Joe, and thank you, everybody.